Today, we are tackling a puzzle that sits at the very core of reality. It's a kind of cosmic accounting error that, once you understand it, unleashes the most powerful force we've ever gotten our hands on. This is the missing mass mystery.
So let's just jump right in. I want you to forget basic math for just a minute. What if you could take two things, add them to two other things, and end up with, well, less than 4? It sounds completely bonkers, right? Like it breaks the rules of the universe. But this exact paradox is the secret to unlocking the incredible power that's packed inside every single atom.
To get our heads around this, we have to go small. Like really, really small. We're going to journey right into the heart of the atom, to its nucleus, which is home to the true heavyweights of the universe.
And here it is, the atomic nucleus. It's this tiny, positively charged, and almost unbelievably dense little ball at the center of every atom. And it's really only made up of two main things.
Meet the nucleons. You've got your proton, which has a positive charge, and then you have the neutron, which, just like its name suggests, is totally neutral. That's it. These two little particles are the building blocks that get crammed together to make that nucleus.
And when I say crammed, I mean it. The density here is it's staggering. We're talking 2.3 times 10 to the 17th kilograms per cubic meter. Now, that's a number so big, it's kind of meaningless. So let's try an analogy. Imagine taking every single car, truck, and bus on planet Earth and crushing them down until they all fit inside a single sugar cube. That's how dense the nucleus is. It's absolutely insane.
Okay, so we've got these super dense cores made of protons and neutrons. Simple enough. But this is where our cosmic puzzle really kicks in, where the math just stops making sense. Let's get to the heart of this missing mass mystery.
So here's the thing that baffled scientists. It's a concept called mass defect. And what it means is this. If you take a proton and a neutron and you weigh them separately, and then you let them combine to form a nucleus and weigh that nucleus, the nucleus is always lighter than the two parts you started with. It's like some of the mass has just vanished into thin air.
Let's use a real-world example. Take a helium atom. Its nucleus has 2 protons and 2 neutrons. Okay, easy. If you add up their individual masses, you get about 4.032 atomic mass units. But when you actually weigh a helium nucleus, it's only 4.0015. So a tiny little bit of mass, 0.0305 units, is just gone. Where did it go? It can't just disappear, right?
Well, it turns out it didn't just disappear. It transformed. And the key to solving this whole puzzle came from, you guessed it, Albert Einstein. He gave us the formula for what you can basically think of as a kind of cosmic glue.
And there it is, probably the most famous equation in the world, E equals mc squared. But what does it actually mean? It tells us something revolutionary, that energy, that's the E, and mass, the m, are really just two different forms of the same thing. They can be converted into one another. And that c squared part, that's the speed of light, squared. It's a gigantic number, which means a tiny, tiny amount of mass can become a huge amount of energy. So all that missing mass, it wasn't lost at all. It was converted into a tremendous burst of energy. We call this energy binding energy. It's the energy that's released when the nucleus is formed, and it's the very same energy that now holds, or binds, those protons and neutrons together so tightly. The mass literally becomes the glue that holds the nucleus together. This is incredible, but it leads to the next big question. How can we tap into this energy? How can we get it back out? Well, it turns out there's a map that shows us exactly how to do it. It's called the curve of stability. Now, I know this might look a little complicated, like something from a physics textbook you try to forget, but trust me, this chart is arguably the single most important graph in all of nuclear physics. It's a map that shows us exactly how stable different atoms are. And reading this map is actually pretty easy. Just think of it like a mountain. The higher up an element is on this curve, the more stable and tightly bound its nucleus is. You can see the very peak is right around iron, which makes it one of the most stable things in the entire universe. Everything else, the really light elements over on the left, like hydrogen, and the really heavy ones on the right, like uranium, they're all less stable. They're down in the valleys. And the key takeaway is this. Everything in nature wants to climb that mountain. Every nuclear reaction is just an attempt to get closer to that stable peak.
And that natural desire to climb the mountain gives us two very different ways to release all that binding energy. And this is where we finally get to fission and fusion.
Path number 1 is fission. This is basically what our nuclear power plants do. You take a really heavy, unstable element from the far right side of the curve down in the valley, something like uranium. Then you split it in two.
The two smaller pieces that you're left with are farther up the curve. They're more stable. And in that process of climbing towards stability, a massive amount of energy gets released. Path number 2 is fusion. This is the power source of the sun. In this case, you start on the other side of the mountain, way down in the valley on the left, with very, very light elements like hydrogen. You take two of them and you smash them together. You fuse them. The new, heavier thing they create is way, way higher up the stability curve, and that even bigger climb releases an absolutely immense amount of energy.
So you see, it's two totally opposite approaches, but they're both trying to do the same thing. Fission splits the heavy atoms, fusion joins the light ones. But in the end, both processes are just a way of climbing that stability curve, and both of them unleash that incredible energy that was once that missing mass.
But the amount of energy you get out isn't the same, not even close. If you look at the curve, the climb up from the light elements in fusion is much, much steeper than the little hop you get from splitting heavy elements in fission, and that simple fact on this graph explains everything. It's why a fusion-based hydrogen bomb is so terrifyingly more powerful than a fission-based atom bomb. The physics of that curve dictates everything. So, the case of the missing mass is solved. That little bit of matter that seemed to disappear, it was never really gone. It was just hiding as the energy that holds the entire universe together. It's a power that can build worlds, or, obviously, end them. We've cracked the physics, but the biggest puzzle is still here. What do we do with a force that is both the engine of the stars and the blueprint for our own annihilation? The choice isn't just about what we will do, but what we should do with power on this kind of scale.
Thank you for watching my video. Please like, subscribe and hit the bell icon.